Okay, so now we know Ohm's law that's going to relate the voltage to the current to the resistance. Now we want to talk about the amount of energy and how much energy is being given off or how much energy is being taken in by a electrical system. And we talked about that in a wire is going to be composed of atoms, and then as the electrons travel through the wire, they're constantly bumping into the atoms. And every time the electron bumps into an atom, it gives a little bit of its energy to the atom. And then that atom will start to vibrate. And when atoms vibrate, one of the things that they do is they give off heat. So the more electricity that flows through a wire, the greater its heat that is going to be given off by it. Now, we had a formula, if you recall, from the previous lesson that said that the voltage was related to the amount of energy per unit charge. So this was our definition of what voltage was. Voltage was related to the energy of a system divided by the amount of charge in that system. So if we were to take this formula and then rearrange it so that it says E equals something, what would it be? So go ahead and do that. So on your little piece of paper, rearrange the formula so that it says energy is equal to something, and then what would you get? Energy would be equal to the amount of charge Q times the voltage. Okay, but we're interested in the rate at which the wire is going to be giving off energy. So that means we need to include the effects of time. So what I'm going to do is I'm going to divide both sides of the equation by T for time. We want to know how much energy per unit time that the wire is going to give off. Well, this is going to be power. So it's a cursive capital P. So that's we can't use this P for power because we're already used that for pressure. So I'm using a capital cursive P to stand for power. And then notice that if I was to take these two things and put them together, what would I get? That would be the current. So power is going to be equal to the current times the voltage. Or I could rearrange it and I could put the V in front, and then I would have that equation over there. So power is equal to voltage times current, or current times voltage. It's the same thing. And as an example, I've got a toaster. So normally you don't want to waste electrical energy in the form of heat. But in the case of a toaster, you do. So the idea is to make the wires in a toaster as resistive as possible so that they resist the flow of electricity. So that means that the electrons are really being slowed down as they go through the wire. They're really going to heat up that wire, and then that's what's going to toast your toast. Now, you don't want that to happen, though, when you're talking about the wires that are transmitting the electricity from the power plant to your house. So it turns out that something like 50% of the electricity that comes out of a power plant never makes it to your house. So, or let me rephrase that. 50% of the electrical energy produced by the power plant doesn't make it to your house because it's being turned into heat that is going into the air from it. Now we can take this formula here, so let's erase this so you can see a little bit better. So now we can take this formula, the power of a system is equal to the current times the voltage, and we could, if we wanted to, we could combine it with this formula here. So if I took this V and I put it there, then I would end up with P equals I squared R. Or I could take this formula and solve it for the letter I, and then put it into this formula, and then I would get that P is equal to V squared over R. So those are two other versions of this formula. So this can be called Joule heating. And for purposes of the exam, don't worry about those other two formulas. It all depends on what you're given in the problem. So if you were given the voltage and the resistance, then the best formula to use would be equation 21.4b. But if you were given the current and the resistance, then the best formula to use would have been 21.4c. But as long as you remember, if you take this formula and you have this formula, you can always derive those other two pieces. So here's an example. A toaster is connected to a 110 volt outlet. It draws 2 amps of current. How much power does it use? So write down what you're given and what you're looking for. So we know the voltage, we know the current, and we're looking for the power. So select the formula that connects the letters, plug in your numbers, and you get 220. Now we need to know what's the official metric unit. So power is going to be abbreviated by the letter P, but it's going to have units of joules per second. But another name for a joule per second is a watt, named after a guy by the name of Watt. So the official metric unit for power is going to be called the watt. So you could have said 220 joules per second, and that would be perfectly okay. But it might be better to say 220 W for watt. And then let's take a break, and when we come back, we'll talk about the kilowatt hour.